Let's use the 6-step procedure from your textbook to draw the graph here of a rational function. Okay, so what is going to make our lives a whole lot easier is to just go ahead and factor everything just right away. We're going to need to factor it anyway to do a bunch of these tasks, so we might as well just do it right away. And let's do that. So first of all, we see that we've got common factor all through the top. There's a 3, so we can take a 3 out of all those. So we got x squared minus x, 18 divided by 3 is 6. Okay, we can now factor this. We want two things that multiply to be negative 2 that add to be 1. Well, it's 2 and negative 1. So we got x plus 2, x minus 1. Okay, and then we can further factor the numerator. So we got 3 times, what is this going to be? Negative 3, positive 2. Okay, so now since we've done this before, we can see into the future that these two are going to cancel out, but we're just going to leave those there for now. We just factor everything right away, and then we can start working on these tasks. So let's take a look at this real quick. This is on page 321. This is our 6-step procedure for graphing rational functions. I've already used this, so I didn't want to print it out again. So ignore the check marks for now because we're not done with any of this. Okay, so let's do the first step. So let's find the domain of R. Well, first thing we do when we find the domain is we note that it is a rational function, and we know that for any rational function, the domain is the set of all the x values that do not make the denominator 0. So what we're going to do to find it is we can just set the denominator equal to 0, and then solve that and find those values. So this is pretty quick, right? We've got two factors in the denominator. Well, if we're excluding values that make it 0, hopefully it's pretty clear. We can see that our domain is the set of all the numbers that are not equal to negative 2 and not equal to 1. So our homework is going to probably want you to write this in interval notation. So it's all the numbers except for negative 2 and except for 1. So we can write that in interval notation. So we go from negative infinity to negative 2. Then we want to go union from negative 2 to 1. And then we have a union from 1 to infinity. So we caught all the values from negative infinity to infinity, excluding negative 2 and excluding 1. So we have our domain. Okay, so now we're on to step 2. We can reduce R to the lowest terms if applicable. So we can do this again pretty quickly because we've already factored everything. We know that when we have common factor in the numerator and the denominator, they cancel out, and well, we're left with our reduced function. So we got f is 3 times x minus 3 over x minus 1. So we're finished there. We ought to also look ahead to when we're finding intercepts, or excuse me, not intercepts, but when we're finding vertical asymptotes and holes in the graph. This is going to indicate to us that we're going to have a hole in the graph. But we'll talk about that here in a second. Okay, so step 3, we want to find x and y intercepts of the graph if they exist. Okay, well we know how to do this too, right? X-intercepts, we're just going to set the function equal to 0, solve for x. And when we do y-intercepts, we always do the same thing. We're just going to evaluate f of 0. So this one's probably going to be the easier one, but we can do both of them. So set the function equals 0, solve for x. So we can use the reduced function for this because the things that we're missing out on from this one are excluded from the domain anyway. So let's just use our when we set a rational function equal to 0, essentially all we're going to end up doing is set the numerator equal to 0. And we've already taken out this value, so we don't have to worry about it. We can just use the reduced function. So let's do that. We've got 3 times x minus 3 equals 0. And again, we know that when we have a fraction, and if we set this equal to 0, our first step is just going to be multiply the denominator anyway, so we might as well just, not, or we could do that in our heads sort of on the way. But anyway, we can solve this one. So we're going to divide by 3 on both sides. 0 divided by 3 is 0, and we've got x equals 3. So probably a little bit too long of an explanation for what's happening there. We just solved where the function was equal to 0, and we got it. So this is an x-intercept. We can write it as an ordered pair. 3, 0. There you go. Okay, now we want to find our y-intercept. So this is just going to be where we're going to evaluate f of 0. So f of 0, and again we can use the reduced function. We got 3, 0 minus 3 over 0 minus 1. So this is 3 times negative 3, that's negative 9 over negative 1. So this is positive 9, and our y-intercept is the point 0, 9. All right. Excuse me, we found x and y intercepts. Got it. Step 4, determine the location of any vertical asymptotes or holes in the graph if they exist. Analyze the behavior on either side of the vertical asymptotes if applicable. So analyze the behavior of r on either side of the vertical asymptotes. I think we're going to end up doing this in step 6 anyway, so why don't we hold off on that? But we can certainly determine the location of any vertical asymptotes or any holes in the graph. Well, let's take a look at, this is step 4. Let's take a look at theorem 4.1, location of vertical asymptotes and holes. Okay, so suppose r is a rational function, which we've got. We can write it like this, where p and q have no common zeros. That's just a fancy way of saying they don't have common factors, which means that it's reduced, right? So in our case, we have a rational function, here it is, and we can reduce it. So we could write it as 3 times x minus 3 over x minus 1. So that's what this thing is saying. It's got no common zeros, so we've already reduced it. Okay, so let c be a real number which is not in the domain of r. So going back to our problem, before we took away this factor x plus 2, we found our domain using these, right? So we took away negative 2, we took away 1. Okay, so in this case, let c be a real number which is not in the domain of r. So in our case, we're going to be using that negative 2 and that 1. Okay, so if our denominator at that value is not 0, then the graph has a hole at that point. Okay, so essentially what this says is if we have a domain restriction and it gets canceled out at some point, that means that there's a hole in the graph. So we do have that, right? We had a domain restriction, which was negative 2. It was removed from our function, or excuse me, the domain restriction was taken away when we reduced it, right? If I put negative 2 in here, it's not going to make it 0. It's going to be a real number. So I can put f of negative 2 in our reduced function. We got 3 times negative 2 minus 3 divided by negative 2 minus 1. So we can crank that out real fast. Yep, so we got 3 times, what is this, negative 5 over negative 3. So then my negatives cancel, my 3's cancel, so we're left with a 5. So this tells us that we have a hole in the graph at negative 2 comma 5. Okay, so again, this came from our domain restriction. Our initial domain restriction got factored away in step 2 when we reduced this. Our domain restriction, didn't really go away, but it went away in the sense that it's not present in the reduced function, right? That behavior that took it away from our domain doesn't exist anymore in the reduced function. But we still have to account for it, which is why it's a hole, and it's not a vertical asymptote. Okay, so our other zero from our other domain restriction that we had to check was 1, and we can see from our reduced function, again pointing at this one, if I put 1 in here, it is going to make that a 0. So this is going to be a vertical asymptote. So we're going to say vertical asymptote at x equal 1. Okay, so we got a hole in the graph at -2, 5, and a vertical asymptote at x equal 1. So again, this came from initially our domain restrictions were our candidates for these things, and whether or not it represents a hole or a vertical asymptote is whether or not that domain restriction got canceled out, right? When we cancel it out, that's going to give us a hole in the graph, and when it remains and it's not canceled out, that's going to be that vertical asymptote for you. Okay, so that was step 4. Now we're going to do step 5. What is step 5? Analyze the behavior, analyze the end behavior of R. So that means we're finding horizontal or slant asymptotes if they exist. So we're looking for horizontal asymptotes now. Let's check out theorem 4.2. So theorem 4.2, location of our asymptotes. Let me get this. Good. All right. So suppose R is a rational function and we've got a quotient of two polynomials there. Leading coefficients are a and b. If the degree of the numerator, right, the numerator, if the degree of the numerator is the same as the degree of the denominator, so that's the denominator, then y equal a over b, so this is the quotient of the leading coefficients, is the horizontal asymptote of the graph. Okay, well, that's the case we're in, right? If we go back and look at our original function, and maybe I'll just rewrite it. F of x is 3x squared minus 3x minus 18 over x squared plus x minus 2. Okay, so we observe that the degree of the numerator is 2, the degree of the denominator is also 2, so that means that they're the same. So that means that y equal the quotient of their leading coefficients is the horizontal asymptote. So we can say horizontal asymptote at y equals the quotient of their leading coefficients. So the leading coefficient in the numerator is a 3, and the leading coefficient in the denominator is a 1. So we've got horizontal asymptote at y equal 3. So something that kind of gets glossed over, and maybe I will try to build this into a future example, something that gets glossed over is whether or not this function crosses the asymptote. There's nothing that tells us that functions can't cross horizontal asymptotes, right? They're not domain restrictions in the same way that vertical asymptotes are. Vertical asymptotes can't be touched by a function, well, because they're domain restrictions, right? But horizontal asymptote, it is entirely possible to touch a horizontal asymptote, and we can check real fast whether or not it does by taking and let's ask this. So does y equal f of x touch y equal 3? So do these graphs intersect? Well, really, that's the same question as does f of x equal 3 have solutions? Because if it does, then those are the x values for which it crosses that line. So we can solve this real quick, and let's go ahead and use the reduced function. So we had 3 times x minus 3 over x minus 1 equals 3, and we're going to find out if this has any solutions. And we can get done with this pretty quickly. So we'll multiply both sides by x minus 1. It gets canceled out here. So we can also divide both sides by 3. So we got x minus 3 equals x minus 1. Subtract x on both sides. And we say, no, this does not have any solution. This does not have any solutions. So that means that this graph cannot touch the line y equals 3. So we can maybe note that graph does not touch. Okay, awesome. So that was step 5. So we found our horizontal asymptote, and we determined that our graph does not touch the horizontal asymptote. Okay, well, let's take a look now at step 6. Use a sign diagram and plot additional points as needed to sketch the graph of our function. Well, essentially this step is just kind of tying everything we just did all together. So let's do that. We can put everything that we just did, we can put it on a graph, right? So let's go back here. All right, so our domain, that was wonderful. Reduce the function, that's great. X-intercepts and y-intercepts, let's put these on there. So we've got 3, 0 and 0, 9. Let me draw a picture here. We've got 3, 0 and 0, 9. I probably made those a little big. 1, 2, 3, 4, 5, 6, 8, 9. Okay, 0, 9 is there. So here are our intercepts. And we know that these are the only intercepts, right? Because we found these in step 3. Okay, we've got a hole now. Step 4 told us we have a hole at -2, 5. So let's put that on there. Here's -2. 1, 2, 3, 4, 5. There is a hole there. Okay, we've got a vertical asymptote at x = 1. X = 1 is this vertical line here. All right, here it is. How beautiful. Horizontal asymptote, we've got it at y = 3. So y = 3 is this horizontal line right here. And I think it looks like we can get away with not drawing any other extra points just because of the way this thing has to look, right? So everywhere that is not a hole or a vertical asymptote, we know that this is going to be a smooth and continuous curve. So really it's just going to come to connecting the dots, right? So let's check it out. So if we went from this point and we moved to the left on this function, we showed a couple of things. We showed that this is our horizontal asymptote. So that means that the graph has to approach it as we approach -infinity and also as we approach positive infinity. Now we know that we can't cross this. We showed this in step 5 that we can't cross this. So if it's going to come from this hole and go toward that asymptote, it's going to have to end up looking like that in some way. In some way. I mean, maybe it goes up a little bit, but it's going to end up going back down here in some way. Okay, and similarly, our graph is going to have to come out of this point, and it's going to have to approach this horizontal asymptote. So, well, it gotta look like this, and it's not going to touch it. So it's got to look like that. Okay, we also know that after it comes out of this hole, we've got to come up through this point here. So we connect the dot there, and then, well, the vertical asymptote, after we leave this point and move to the right, it's either going to go up or it's going to go down, right? That's the way vertical asymptotes work. We're going to approach the vertical asymptote as we approach that x value. Well, again, we showed that we can't cross the horizontal asymptote, so that means it's forced to go up here that way. So, if we're given the choice of two things and we show that this can't be, that can't happen, well, it's got to be the other one. Okay, so now we've got the same idea here, right? We know that we can't go up because we can't cross that asymptote, so we've got to go down toward that vertical asymptote. So there we go. We did it. We graphed our nice rational function using the 6-step procedure.